TP squared. I'm then going to multiply top and bottom by 1 over c squared to put it in a more traditional form. So on top, I'm left with TP squared, and on the bottom, I'm left with 1 minus v squared over c squared. And then square root both sides. So time is equal to the proper time divided by the square root of 1 minus v squared over c squared. This 1 over, which I can write as 1 over the square root of 1 minus v squared over c squared times dp. This right here shows up so often in what we're doing, what this is the introduction to, that it has a special symbol, the gamma, lowercase. And this is known as the Lorentz factor. Lorentz, over the course of the next several decades after Maxwell, before Einstein, Lorentz actually derived almost all of the math for what's now known as special relativity. He just would not make the final leap of faith saying the speed of light was the same. He was trying to justify why you won't notice that why it looks like time is different, but he refused to accept the fact that time could be different. And so time is equal to gamma times the proper time. So time is relative. Time depends upon how fast you are going. If you got in a car, came up, so you and a twin, let's say you were born at the exact same time, just for the sake of this. You were born at the exact same time, although I think it's biologically impossible, but let's just assume. Conjoined twins, born at the exact same time. And then one of you drove away and then came back, and the other one just stayed where the person was. The twins are no longer biologically the same age. That's the implication of this. If I ran from my office to here, I would not age as much as those people who were just sitting here in the room. Because the faster I travel, the slower my time is.
Are you saying if I keep running, I will ever age?
No. I'm saying you will not age as fast as someone who is not moving. And I'm not talking physical fitness or anything like that he will live longer because he is healthier. We are talking about the fact that biologically the times are not the same. There was an experiment done in, I think, 1971. They took 2 atomic clocks and synchronized them up to the nanosecond. They put one on a plane and flew around the world going east to west, and the other one went west to east. And they did 2 tests. So one, worded badly, try that again. Took 2 atomic clocks, put one on a plane, one at the Air Force Base. One of the planes went east, flew around the world. I guess the way I just do it from my point of view, went west around the world, and then they compared the atomic clocks. The atomic clocks were out of sync. They did the same experiment going east. Atomic clocks were out of sync again. There's some other experiments that we'll get into later, but the implication that time is not the same. This has real world implications. Satellites from GPS, as they're traveling around the world, they are traveling a lot faster than we are on Earth. Their time is slower than it is for us on Earth. And so that has to be taken into account. Otherwise, I think that they would go off 30 meters a day. So, questions to hear?
So if they got out of sync, then would,
Sorry?
if the GPS was like behind 30 meters a day, then what would that do for GPS?
Make it completely worthless. I guess you could predict on such and such a day it'll be accurate again. But from a military point of view, you'd have a hard time finding your targets. From a social point of view, geocaching would not be a thing.
So does that mean satellites are aging more slowly than they would if they were traveling at the same speed? I mean, like
Then if they were sitting on Earth,
like needing maintenance less
yes,
often.
they would not be aging as much. Now, because of what they are doing and the size of the Earth, I mean, 30 meters doesn't seem like much if you think about the entire circumference of the Earth.
Yeah.
So it's getting off by microseconds.
Okay.
So it's not a huge impact, but it's enough of an impact. We'll calculate that later. Other questions right now? All right. So, for the first couple of years, when I got to this point, we would then launch into special relativity. We do the twin paradox. There were some classics of it. Then I had a student who later on needed to know about AC and not air conditioning, but alternating current. And so I've now taken, it flows so nicely into special relativity, not general relativity, special relativity, but we are going to jump back into alternating current. And then we will meet up with this again. Oh, one other thing while we're here. You notice that this Lorentz factor, what would happen if an object's traveling the speed of light?
It would never age.
What mathematically?
You'd have 1 divided by 0.
Yeah. And the math people really haven't figured out how to do that yet. So this is why the physicists claim that anything traveling slower than the speed of light will never actually get to the speed of light. Anything traveling faster than the speed of light will never get as slow as the speed of light. So it's sort of this, the only things that will go travel the speed of light are massless particles. So this is an example of sort of the math driving, coming out of the math drives the idea that speed of light is a barrier.
So humans can never go the speed of light.
Sorry?
Us humans can't ever go like be as fast as the speed of light.
Right.
That's a shame.
In a vacuum, that is. I have traveled faster than the slowest we've ever gotten light. Because in a right medium, the speed of light, the speed of light will get smaller. And I think it was in graduate school when they got it down to like 6 meters per second. I have gone faster than that.
Nice.
Not in that medium. So what would happen if you actually had something traveling faster than the speed of light in a medium? Can't do it in a vacuum.
I guess you can see it.
No, actually you can see it.
Okay.
Yeah, wouldn't everything like really slow? Like time. Anyway.
What happens when you travel faster than the speed of sound?
Boom.
Yeah,
So it'd be a
you have a buildup of pressure waves. You do actually have a buildup of light waves, and it's called Cherenkov radiation. It's a blue glow.
So would there be a light boom?
Would be a say.
The sonic booms, would it be a light boom?
It's generally not called that, but an optical boom more likely. But you do get a special kind of radiation coming off of it.
That's cool.
How do you spell Lorentz again for the Lorentz factor?
I think it's Swiss. I think.
It's like a shorter wavelength, maybe that's what it's called.
I'd have to go back.
Wait, so we would never go
Because
to
it's sad. I'm not sure.
ever.
If they're correct.
So honestly,
Well,
we would never ever go like be as fast as speed of light. Ever.
right. Give me a hypothetical situation in which you could do that.
I just want Star Wars to be interesting in the first place.
Sorry, you can never, all right, so let's talk what is actually theoretically possible, not realistic, but theoretically possible,
Okay,
and with our current knowledge.
okay.
The math is telling us we cannot travel faster, if we start below the speed of light, we won't get above it, or get to it or above it. If you start above it, you can't get below it. In terms of things traveling faster than the speed of light, yeah, you would end up with an imaginary answer, but imaginary answers don't phase physicists. It just has a different physical meaning. So there is a theoretical particle called the tachyon, which travels faster than the speed of light. The tachyon has never been seen. It's just theoretically it's possible. Again, the theorists go, well, it's not unallowed, so let's play with it. And if they ever find it, then you have physicists hail to zeros, and if it's never found, it goes on the scrap heap along with most of the theoretical work. So the tachyon particle, if you watch Star Trek, it occasionally shows up there. Tachyon gun, we'd probably have to redefine time. If I shot you with a tachyon gun, you'd be hit by the tachyon before I pull the trigger, because time sort of loses some meaning there, or has to be redefined. Now, from a pre-Einstein point of view, if I apply a force to an object, I give it acceleration, a net force to an object. So theoretically, if I applied a constant force to an object, the acceleration would be constant, and therefore it would just get faster and faster and faster. Why not exceed the speed of light? The trouble with that is that as it gets faster and faster, the mass starts to change. And this is the difference between rest mass and mass. That the mass starts getting bigger the faster it goes. And so as it approaches the speed of light, it becomes so incredibly massive that the same force causes less and less acceleration. And so what would happen is, if you applied a constant force, then speed versus time, that's the speed of light. So with a constant force applied, it would start to do that because the mass becomes so huge. And acceleration, which is the slope of this, starts getting closer and closer to zero. So that's what they've come up with. A number of years ago, somebody thought that they might have exceeded it, and they felt that there had to have been a mistake somewhere. This was 5 years ago or so, and so physicists were not willing to say that they had actually violated this, what was generally considered to be a standard. The press got a hold of it and said, "Oh, somebody broke the speed of light. Einstein's wrong." Physicists said, "Where's the mistake?" And someone had said, the people who came up with the value took into account more things that, according to one physicist, they took into account more things than anyone had done before, trying to explain it. It came down to there was a piece of equipment that had an issue. There's enough evidence to support that we aren't going to exceed the speed of light, that there had to be something there.
So no Star Wars.
All right, so Star Trek. There was actually a talk at Wake Forest a number of years ago where they talked about how could we do faster than light travel? How do you do it? So one of them is warping space itself, which is what they do in Star Trek. They don't officially exceed the speed of light, they just appear, it just appears so. So if that's space right there, and I want to get from here to here really fast, if I can warp space so that these 2 points come closer to each other, so then all I have to do is travel that distance, and it looks like I traveled a great distance in a little bit of time. And so that theoretically is possible. The energy in order to do that would be greater than, well, basically the energy of the Earth. If we could somehow convert the entire Earth into pure energy, that would not be enough in order to be able to do that.
So basically in Star Trek they tesser?
They
Tesser?
said tether?
Tesser? Wrinkle in Time.
Oh,
Tesseract.
it has been way too long since I've read Wrinkle in Time.
Basically, it's explained in the book that you travel in the 5th dimension, making
Oh.
the 2 points come together.
Yeah, that in essence is what they've done.
Cool.
That's what can happen, alright.
Now, there's also the idea of what we just talked about, you travel really fast, then you don't age as much. So in Star Trek, if you're traveling near the speed of light, why is not everyone dead by the time they get back? But there's also theoretically, you could create that time warp bubble where the time is different in an area, in a volume around the ship. So if you got the ship here,
Nice.
you basically create a warp bubble around the ship, so there's no massive aging issues. Again, theoretically possible, as long as you've got some unlimited energy supply.
Yeah, is that possible? It's possible.
Now, is it gonna happen in my lifetime? Not expecting it. Your lifetime? Really not expecting that either.
It sucks.
Ever?
Maybe.
Who's to say?
Who knows? We'll see. If that does happen, though, that's gonna be so cool.
All right, other questions right now?
So like, you know the thing where it's like, so if I told my grandchild, right, to come see me right now, I wrote him a note, sooner or later, let him to time travel here, would he do it?
All right, so let's talk theoretically possible. Theoretically, from what I have seen, it is possible to build a machine that can start tracking time so that you can jump back and forth through time.
No.
But you cannot jump to before the machine is built. So until the machine is built,
Get on that.
so
Like teleporting or like through
you
time?
could, it's a
Time
quantum theoretical, this is theorist, very little grasp of reality kind of thing. So if the machine has been built and we don't know about it, then perhaps your great to the 100th power grandchild could come back, but
So you're saying that endgame could be possible?
I'm not sure I can address endgame.
Wait, no, didn't they build it after?
Well, they use the technology that had been built before.
Now, when you start getting into the Marvel universe, there's something known as the superhero exemption. So,
Everything was.
Everything's normal.
sure.
And then that is a great segue to leave.
It's a Marvel.
That is. Yes.
We have talked in the past about, this is a DC power supply. And for the purists out there, just get over it. All right, DC power supply. Because things are basically, you have current traveling in one direction. This is an AC power supply. The symbol recognizing the fact that the current is going to be alternating back and forth. So here, you'd have current flowing across the resistor and then back and forth. The other thing, and the very little time that we have remaining, there are several ways of analyzing it. One of them gets into using complex numbers, and we're going to avoid that. Instead, we're going to use something known as phasors. We'll be doing phasor diagrams. So instead of dealing with complex numbers, we're going to be doing a bunch of, with some you know, Pythagorean theorem, some geometry. Not much to drink. A phasor is an arrow which spins in time, which makes it sound more exotic than it is. That everything, the second hand there is something that is moving in time. We're going to set up an axis. A phasor looks a whole lot like a vector, except the phasor spins around. Because as you're dealing with the power supply, because something's oscillating back and forth, we're going to take this oscillation back and forth and convert it into rotational motion. Size of phasor is equal to the magnitude of the vector, or equal to the magnitude, not necessarily the vector. And the projection onto the x-axis, projection onto x-axis, is the instantaneous value. And this is leading to the lab, where there's one part, if you get 1% off, you've done something wrong. I just want you to experience a lab where 1% is too much. And we'll end on that note. Oh, I have stuff to hand back. So I guess we'll end on this note. What is it, Brenda? Yeah, I've got master set in here too. Aaron. Carly. There you go.